Good day to Dr. Chow. I'm Hor Wai Keat, and here I'm with my lab partner is going to present about our embedded system project with the project title of 8-bit microprocessor project. First of all, I'll be giving an introduction on our project. So we are required to design a simple 8-bit microprocessor that's capable to perform 7 instructions using VHDL code in quarters prime light and validate the results with model sim waveform diagram and also Altera DE10 standard development board that is available in the lab. Here are a few design assumptions and specifications and assumptions made in our project. First of all, there is only a single 8-bit bus used in our project, and the data path is in 8-bit form to perform 7 operations. The opcode is 3 bits wide, and the operand takes 5 bit. Since there are only 5-bit operands, therefore there are only 32 addresses used, and we are using register direct address type. In our design, we assume the program and data executed are stored in memory, except the results of rotate left operation, in which it will be stored in the accumulator. And now I'll be continue with the design implementation of our project. And here is the block diagrams of our system. So memory such as SRAM is commonly asynchronous, therefore synchronous registers will be included as buffers between the memory and the bus for both address and data signals. The registers are memory address register MAR and memory data register MDR. Arithmetic and logic unit performs arithmetic operations and outputs result as well as the flags. Accumulator SCC is a register that holds the result of arithmetic operation. Program counter PC is used to store address of next instruction, and it also includes necessary logic to automatically increment the address held in the PC. If a branch is executed, the program executes out of sequence, so it must also be possible to load a new address into the PC. The instruction register IR holds the current instruction, and the bits corresponding to the output are input to the sequencer, which is the state machine controlling the overall function of the microprocessor. The sequencer will then generate the control signals to determine which component can write to the bus, which register are loaded from the bus, and which ALU operations are performed. And here's the SM chart of our design. First, the execution cycle can be divided into 2 parts, fetch cycle and execute cycle. The first state of fetch cycle starts with the contents of the PC are loaded via the bus into MAR, and at the same time, the address in the PC is incremented by 1. Then in state S1, the CS and R_NW signals are both exerted to read into MDR the contents of the memory at the address given by MAR. In state S2, the contents of MDR are transferred to IR via the bus. In the execute phase, the instruction now held in IR is interpreted and executed. In state S3, the address part of the instruction, the operand, is copied back to MAR in anticipation of using it to load or store further data. If the opcode held in IR is stored, control passes through S4 and S5, in which the contents of SCC are transferred to MDR and then to be written into memory at the address previously stored in MAR when CS is exerted. If the opcode is not stored, CS and R_NW are exerted in state S6 to read data from memory into MDR. If the opcode is loaded, the contents of MDR are transferred to SCC in state S7. Otherwise, it will check if the opcode is B and Z. If the opcode is B and Z, it will check if the Z flag is raised. Otherwise, it will check if the opcode is addition. If the content of SCC is not 0, Z flag will not be raised and MDR will be loaded into the PC, else it will branch back to state 0. If the opcode is addition, an addition operation is performed by the ALU using the data in SCC and in MDR, else it will check if the opcode is subtraction. If the opcode is subtraction, then a subtraction operation is performed by the ALU using the data in ACC and in MDR. Else, it will check if the opcode is XOR. If the opcode is XOR, then an XOR logic operation is performed by the ALU using the data in ACC and in MDR. Else, it will check if the opcode is ROTL. If the opcode is ROTL, then a rotate left operation is performed by the ALU using the data in SEC. And now I'll be continue with interface and specification list of our design. Here is the list of interface with description. The important interface will be clock, which is the periodic waveform of high and low signals, reset, initialization of all sequential blocks, sec flag, zero flag. When false, content of MDR will be loaded into PC. OP, number of instruction based on number of bits, which is 2 power of n equals to number of instruction. Sysbus, connection between all the components. ALU ACC, load ACC with result from ALU. ALU add, perform an addition operation in the ALU. ALU sub, perform a subtraction operation in the ALU. ALU bit XOR, perform a XOR operation in the ALU. ALU ROTL, perform a rotate left operation in the ALU. And now I'll pass the floor to Sia Wei Jin to simulate our design in Model Sim.
Thank you, Wai Keat. So now I'll be simulating the result using Model Sim. Okay, so first, this is our code, and let's simulate the synthesized circuit schematic first. So as you can see, our CPU is made out of 5 components: the instruction register, the ALU, the sequencer, RAM, and also program counter. And we have 2 inputs, clock and reset, and also 1 output system bus. So next, let's simulate the state diagram. So as you can see, we have a total of 10 states. So first we start with state 0 and move on to state 1 and state 2 and also state 3. So state 3 onwards is which state we branch to depends on which opcode of the operation that the CPU is going to do. So without further ado, let's simulate the waveform using Model Sim. But first, we will be simulating the first part with sec flag equals to 0, and we'll see what happens. Okay, so the initial condition, everything is 0. And then we'll load the first instruction into the instruction register. So this is the instruction. As you see, the opcode is 000, which stands for load. And this is the address. So we'll load the content of the address into the accumulator. That's why we got the content of 2 inside the accumulator. And next, the program counter will increment by 1, which will move on to the next instruction. So the next instruction is 010, which is addition. And we'll be adding the content of the accumulator with the content of this address. So the content of this address is right here. So we add with the content of accumulator, which is 2, and the final answer we will get this answer, which is 1E in hex. So what's the the program counter will increment by 1 again. We've got 2 now. Then moving on, the next instruction is 001, which stands for store, and we'll be storing the content of the accumulator inside this address, which is 0C. And moving on forward, the next instruction is the program counter increment by 1 again. Okay, so you got 3 right now. And the next instruction is 011, which stands for subtraction. So we'll be subtracting the content of the using the address with accumulator. So the content of the subtraction is this 1001, 011, which is not 0. So the program counter increment by 1 again. And the next instruction is 100, which is branch if not 0. So as you can see, because of the content of accumulator is not 0, the Z flag remains 0. So it will branch because this instruction is branch if not 0. So because it's branch, the content of the MDR will be put inside the program counter. So in this case, the content of the MDR is inside this address is 0110, which is 6. So previously our program counter is only 4, and now it become 6. So the 5th instruction is skip. So the 5th instruction in our case is the loop instruction. So you will skip it, become rotate left. So in this case, we'll see, you see, it skip the load instruction, become rotate left. So rotate left. We will rotate left the content of 0C. So the content of 0C is this 1E, which is also the result of the addition just now. Rotate left by 1, we will get 00111100. As you can see, is correct. Then the program counter increment by 1 again, so now it's 7. So the next instruction is 101, which is bit XOR. So we will use the content of the inside this address to be XOR with the accumulator. So this is the content of the inside the address, or 011. A bit XOR with 00111100. We will get 00 everything 1, which is in this case is correct. Then afterwards the program ends already. So now we'll be simulating with the Z flag equals to 1. So in order to simulate that, we have to change the content of the subtraction to be exactly to get 0 for the accumulator. So previously the addition, the content of the addition and is 1E. So we have to subtract with 1E again, which is in decimal is 30. So we'll get we'll get 0. So let's see what happened. So for the Z flag equals to 1, the result is same up to the subtraction phase operation. So we can ignore all the result up until here, the subtraction operation. So because just now we already put the value of 1e inside this address, which will be used to subtract. So 1e subtract with 1e will get 0. So as you can see, the Z flag is raised, become 1. So if the Z flag is raised, it will not branch, it will go back as normal. So that's why we can see it will go to the next instruction, which is loop. It won't skip this instruction. So you will load the content. You will load this content inside the accumulator, which is 6. And then moving forward, it will be all the same: rotate, left, and read XOR. So now let's see the memory list before and after execution. So this is the memories before execution. Because we only have one store operation, so only one address will be changed, which in this case is 0C. So let's see how it changed. So as I see, just now it was 0, now it become 1E, which is the addition, the result of the addition, and then we store it inside this address. And that's all for me. Let's move on to the D10 evaluation board result.
Sorry. Hold on. Okay.
So we have simulated the result using the D10 standard development board. First, we simulate using Z flag equals to 0, and this is our result. And now we simulate again with Z flag equals to 1, and this is our result. Okay, now I'll pass to Wai Keat again. Thank you.
Okay, I'll be continuing with the discussion and conclusion of our project. So in the discussion and conclusion part, we will be discussing the challenges and constraints faced in our project. First, there are only 7 operations used in this project, and maximum 8 operations can be performed as there are only 3-bit opcode. Then there are only 32 addresses used, which is quite limited due to 5-bit operands, and no user inputs are allowed in our design other than a reset button and a clock. The branch operation is also limited, which in our design we only use to branch if the values is not 0. Okay, that's all from us. Thank you.
Thank you.